2. سامعني؟ هل انت سامعني عندك؟ متأكد؟ طب بص، هل انت سامعني كده؟ كده سامعني عندك؟ مهم. طب وكده مش سامعني؟ ها؟ سامعني دلوقتي؟ ايه، لا بس انت سامعني دلوقتي؟ سامعني كويس صح؟ اوكي. يوسف، قول لي انت سامعني في البودكاست ولا؟ اوكي، شكرا. podcast, but I'm very happy that we did this. It's actually a dream for a lot of people now to meet you, huh? So I will do a short test for the podcast. يوسف انت دلوقتي شايفني انا وكن صح؟ وهل سامعه؟ Can you speak to me, Ken, please? Because we need to test this podcast.
Sure, let's test it.
So can you hear me?
I can hear you fine. Yeah.
يوسف انت سامع هو كمان؟ Okay, so it works very well. So I will just prepare everything, and we will start when the people join.
All right. Get better. Of the level of complexity is better. So I might take like drying and binder migration, one of my favorite topics, or you think that mixing is easy, but it's really not.
Yeah.
Taking something like that and talking about that. I mean, there are so many steps, and there are so many steps to gain expertise in. Nobody's an expert at all of it. It's impossible.
That's right. So
So where are you in Ken? Are you in
I'm
California?
in Reno, Nevada. I am in the United States.
Okay, perfect. Yeah, I'm also in the United States. I'm in Connecticut.
Oh, we're
Yeah,
in Connecticut.
yeah.
Okay, perfect. So our podcast is ready. I guess people can see this. So whenever you're ready, Ala, inshallah, we can start.
Okay, yeah. I think I'm ready. So yeah, I'll maybe start in a couple of minutes, or maybe in
Okay.
just 1 minute. Yeah, I will just go live now and make introduction. Sorry, Ken, I will just for the first 2 minutes I will be speaking in Arabic, and then I will convert to in English for the audience. Yeah. Okay, let's start. Okay, go live. السلام عليكم جمهور علماء مصر، يا رب تكونوا بخير. النهارده ان شاء الله معادنا مع مقابله مع دكتور كين ودكتور محمد عن لقاء تكمله على لقاء الطاقه، تخزين الطاقه. استاذنكم بس قبل ما نبدا بتعريف المحاضرين، لو بس تقدروا تبعتوا لي تعليقات او ان انتوا شايفيننا او سامعيننا. عظيم جدا، انا شايف الناس بدات تدخل. تمام، شكرا يا ليس. تمام، طيب هنبدأ على طول. طيب أنا يعني طبعا أنا هبدأ المقدمة بس بالعربي للناس. هو طبعا دكتور كان يعني ما بيتكلمش عربي، فهبدأ مقدمة بسيطة، وبعد كده يعني هسويتش الإنجليش. طيب برحب بكم تاني. احنا المفروض النهارده إن شاء الله لقائنا دكتور بالتعاون مع الطاقة بالعربي مع دكتور محمد الخضرجي، واللي هيتشرف باستضافة الدكتور كان، وهنتكلم أكتر عن يعني تخزين الطاقة في أمريكا والثقافات المختلفة. إن شاء الله يكون لقاء مميز جدا جدا. مش هطول، هحاول اكونفرت بسرعه عشان الضيوف ما يزهقوش. Yeah, I will now convert in English. So today I'm honored to be hosting Egypt, Egypt scholars and Taqa BelArabi and Dr. Ken from Gigafactory, and talking about battery storage and the challenges for the battery storage in Germany and USA. So I think it will be a very exciting webinar, and I'm looking forward to see all the people like having discussions and attention with the attendees. So yeah, the mic is yours. Thanks, Dr. Mohamed. Thanks, Dr. Ken, and it's my pleasure to see you here. Yeah.
Thanks a lot, Ala, and thanks a lot, Ken, for being here. So I will do the second introduction. So today it's not my role to give any information. I guess Ken is the one who is mainly will be giving information for all of us, including me myself. So I was waiting for this opportunity to learn a lot from his experience. So Ken had his PhD from the MIT, and then he participated in many roles in the battery industry in the last period of time. In the first Tesla Gigafactory, he was part of the team of the first Tesla Gigafactory in the US. Then he worked as well in many other aspects related to lithium-ion battery manufacturing, especially cell manufacturing in Europe, namely Northvolt, which is located in Sweden. And now he's back based in the US. And we are today focusing mainly on the battery manufacturing, cell manufacturing topics, and the Gigafactory aspects. So we will be discussing mainly on our agenda 3 main points. But as mentioned, I would like to thank Ken for the time. And I would like to mention that I proposed to other people as well to join us internationally, and Ken was really the fastest, and just by proposing the idea to him, he accepted it. So thanks very much for this opportunity. It means a lot for all of us in the Arab-speaking countries and in the Middle East especially. The 3 points which we will discuss, I will just give an overview of our agenda, and then we will go through it one by one. So the first point is that we will try to get from the experience of Ken about the cell manufacturing steps. I guess a lot of people here doesn't know much about cell manufacturing. So we'll try to give like a semi-crash course about cell manufacturing, so to say. And Ken will highlight for us the challenges which are facing lithium-ion cell manufacturing, trying to answer the second question, which is what is the main challenges we need to take care of if we need to produce cells in different regions of the world, like namely the Middle East, for example. So a lot of people looking forward to produce, asking themselves the question why we don't have until now one gigafactory in the Middle East area, for example, for cell manufacturing for lithium-ion cells. And we will try really to jump to the third point of giving a general career advices for the young professionals like myself and the students, whether they are PhD students, university students, of having a career inside the battery world. And Ken was responsible for really hiring a lot of people in the past. So we would like to know his opinion about what he's searching in candidates and trying really to fill the gap. So those are the three main points I would like to propose. So again, thanks a lot, Ken, and pleasure to have you.
Great, thank you very much. I'm honored to be here and honored that you asked. I do feel that, you know, obviously I'm with my gray, slightly balding hair. You know, I'm nearing the end of my career, but when I was younger, many people took their time to spend with me to help me build my career. So this is part of it. This is what people do for people, and I'm always happy to help out. So
thanks, Paul.
Yep. With that, I think you probably wanted to dive into cell manufacturing, and maybe you could bring up an overview. But I'm going to give a couple of generalized statements to set the stage, and they are going to come across as very negative, almost like I'm talking everyone out of doing lithium-ion batteries. And I say that because I don't want you to think that I think doing battery cells is a bad idea. It's because almost everyone I have ever met who has not been in cell manufacturing for at least a couple of years completely underestimates how hard it is. Mm-hmm. It is really hard. So I'm going to give you some examples to set the stage. Then we'll get into the technical side. Again, I don't want you to take this as extreme negativity. Oh, he doesn't think, you know, anyone else can do it. Oh, yeah, that's not what I'm saying. Take it as a challenge. Okay. Take it as a challenge, but take it as a warning as well. So when we set up the first Gigafactory with Tesla, and the partner for cells was Panasonic, and I was in the cell quality group. So we would tear apart cells, we'd open them up, we'd look at the quality, we'd test cells, and so we had a pretty good idea how different companies' cell quality was. And I would argue, certainly then and probably still, for the cylindrical cell format, there is no higher quality cell manufacturer in the world than Panasonic. Mm-hmm. Not just because they've been doing it with all their acquisitions effectively the longest, but the Japanese are very meticulous about details. That's a culturalist statement, I realize, but it really shows in, you know, from the Toyota production method, right? I mean, they've really refined how a lot of these production processes go. So Panasonic take my word for it, that Panasonic was and probably still is the highest quality and most competent cylindrical cell manufacturer in the world. They come to Nevada. They install manufacturing equipment in a brand new factory. Panasonic's manufacturing equipment is co-designed by Panasonic. So it's not like they're just buying garbage off the shelf. They are buying high-end equipment that their own engineers have co-designed, so they know exactly how it works. They know how all the parts go together. This is why their manufacturing so good, because they're not just doing production on somebody else's equipment. They're doing production on their equipment. I think Hirano makes the coders. They maybe don't design the coders, but the cell assembly stuff. So it's Panasonic co-designed equipment, brand new equipment from Japan. They fly, it was at least 250 experienced cell manufacturing technicians and operators from Japan with translators to help train the Americans.
Yeah.
The Americans being part of the problem, because I will tell you, Americans, we're not that great at manufacturing. So you have, and I'm not talking they flew over trainers. They flew over, in Japan, the guy who sharpens the slitting wheel that slits the electrode, he's been doing it for 12 years, and is proud to come in every day to do it. I mean, this is the essence of great manufacturing. So they fly like 250 of them over for 6 months to train the Americans. The factory starts up, and this is public record. They then proceed to lose money every single financial quarter for 2.5 years.
Wow.
Okay. How is that possible? And the short answer is, making cells is really hard. You don't just buy great equipment, hand workers work instructions, which Panasonic did more than that, pour materials in one end and have cells magically pop out the other end. It is so complex. And really, when they finally got to profitability, which they've been profitable, I think, every quarter since then, I can't tell you what the yields are because I'm not allowed to, but basically it was just a battle of getting their yields up, meaning how much product was in spec versus how much product just barely missed or missed specification at any particular step. And every single step of the cell manufacturing, of which there are probably thousands, every one, there's a team battling, with an axe or a hammer, trying to hammer down, get the yield up and figurative hammer, not hammering, but really working to get yield up. And it wasn't like they just solved a problem and were profitable. It was hundreds of problems, not because the equipment's bad, not because Panasonic doesn't know how to make cells, but really, you had new people on equipment. They got training, but there's this knowledge that really helps. And I think part of the mistake that people make in this day and age is they think everything's very automated, which it is. There's sensors, there's cameras, there's inline X-rays, there's, all this super fancy equipment. And they think that means that people aren't important. And that turns out to be very wrong. Yes, in an ideal world, we would have robots make everything, but it just doesn't work that way. So another example, then let's take, and this is hearsay, meaning, let me translate that. This is what I have been told by somebody who was told something. So this may or may not be accurate. But from what I heard, LG Chem, when they set their plant up in Poland, LG Chem, by the way, also a really experienced, great battery manufacturer, and they set their plant up in Poland. They basically had the same problems. Not necessarily the exact same technical problem, but they had yield problems for the first 2 years because new employees on a new line. And then you look at startups, of which I've worked at several, and guess what? They also have problems. And it's not because they're startups and they don't know what they're doing. And that's what people seem to think, is they say, oh, these startups, they don't know what they're doing. But it's interesting to see the established manufacturers also struggle on new factories. It's really across the board. I think as we build more and more of these, we will learn how to learn and we will get better at it. But with that sort of dire warning, let's dive into cell manufacturing.
Yeah, but before we dive into cell manufacturing, this is very interesting, two examples, huh? Because the first thing, let's take the first. I have few comments on this two stories about Panasonic and LG. So I guess you meant when they fly to Nevada to build up the first Tesla factory, right? This was in cooperation with Panasonic. So they had to fly, you said 250 Japanese people plus minus. Is it because the lack of experience, or is it because that they do not trust that no one else will be able to run the manufacturing the way it should be?
No, it was simply it was the lack of, it was the first. It was the lack of experience. I mean, you set up this factory and you hire people. The phrase is off the street. You're not really hiring them off the street. You know, you have a job fair and you hire engineers and you hire operators, and you know, one person may have worked in a paper mill, or one person may have worked, you know, on an assembly line making air conditioners, and somebody else, you know, and people with reasonable experience, but not making batteries. And you say, so what? So if your job is to take this thing and put it in here, and I write you a work instruction and say, you pick this up with the left hand, the handle has to face this way, you pick this up, you inspect it, you put it in there, that's that step, do it. And you say, great, but it doesn't work right. And why doesn't it work right? Well, because they don't know what the cup's made of, and they shouldn't have to know what the cup's made of, and they shouldn't have to know what this is, and they shouldn't even have to know why they're doing it. They're just doing, you know, they're just doing their task. But the interesting thing is, and this is some weird human psychology thing, it does matter.
Mm-hmm.
It really does matter that your people have to understand why they're doing what they're doing. On paper, it doesn't matter, but in reality, you get better quality, better yields, better output when the people who work on your production line, or the engineers or the designers, understand the motivation of why. Now, look, anybody on this call clearly cares, right? So you've got the intent, but you also need to understand, you know, let's say you were an engineer and you were the engineer in charge of mixing. Okay, so you're a production engineer, and we'll dive into production in a moment. You're in charge of mixing. Well, mixing what? Well, you make a slurry. You take your electrode materials that are going to be on the anode or the cathode. You mix them up in a slurry, a wet slurry process, and that happens in a certain order, at a certain temperature, over a certain time period. Some mixes take 4.5 hours to get done, some 6 hours. And you say, well, it doesn't matter because you're a production engineer. The recipe I have says that first I add this amount of this, and then I add this amount of this, and I dry mix it for this long, and then I add some liquid and I mix it for this long, and then I add some of this powder, and then I add some pixie dust, and I mix it for this long, and then I measure my properties with a complex rheometer, and I get these properties to prove that my quality is good, and then I can send it to the next step. I am telling you that's not good enough. Because if that process engineer doesn't understand why these get mixed dry first, why then the liquid is added, why this other thing is added, and you have to wait before adding the other thing. If you don't understand why, it makes troubleshooting really hard. It makes it just doesn't work as well. Your yields aren't as good. And when that engineer and the operators, especially, don't undervalue your operators, when they understand why, then they are cued in saying, well, that doesn't look right. That doesn't look right. And they catch stuff. But if you treat them like little chess pieces that just are supposed to move from one, oh, this is a pawn, they only move this way. Oh, this is a rook, it only moves this way. And you treat them like that, you're going to get exactly what you deserve. You're going to treat your workers like little chess pieces, and that's exactly what they're going to do. They're going to act like little robotic chess pieces, and they're not going to. How's that saying? French guy, Yvon Chouinard, he had this saying, take care of your people and they will take care of your business. Now, look, we're way off the technological part of what. Now I'm getting philosophical. Let's get away from that. Let's get into the technical. We can have a whole philosophy discussion when we talk about career development.
That's right. That's right.
Okay, but I'm going to make you pull up something else. Do you have the mixing? I know I saw you had a mixing slide.
Yeah, that's right. I have the whole processes here from this nice guide, and mixing. We have to search for it. Operating vacuum, dry packaging.
You know what? I can talk it through anyway. But the mixing, the coding, and the drying comes before calendaring. Okay, so actually, let me ask you a question. Is everyone on this call probably read in enough on battery manufacturing that they
know
what an anode and a cathode is? Because I can explain it pretty quickly.
You can do this. Feel free to do it.
Okay. So you all know that a battery, you can charge it and you can discharge it. And I'm speaking in generalities. So there's always exceptions to what I'm going to say. But in general, take what I'm saying as faith. There are exceptions. So some things I say won't be exactly accurate. So a battery cell, think about your little, I wish I had one. Maybe, let me, hold on.
Okay.
No, I can't find it. I was looking for like a little AA battery cell, right? And there's a little dot on the top that's the positive, and then the can, the whole can that's covered is negative.
Yeah.
Negative what? You know what? You don't need to be an electrical engineer. There's two sides. There's a positive side. There's what we call by convention the positive side, which is going to be the cathode, and the negative side, which we're going to call the anode. And new people mix this up. Well, here's your way to remember that. Some people like cats. If you like cats, you're positive about them. Therefore, the cathode is the positive electrode.
That's a very nice way to remember it. Because even me, I used to make them for a long time, but then I had to remember it, in a certain way, that cathode is the positive and anode is the negative,
Yes.
But this is a nice
I'm not saying you have to like cats, but some people like cats. I like cats. And if you like cats, then you're positive about them. That's the positive electrode. The anode is the other one, so it must be the negative. Okay. The cathode, let's start with the anode. The anode, the negative one, in a lithium-ion battery, again, there's exceptions to this, there's so many exceptions, is generally made with three types of components. The main anode component is graphite, okay? And that can be synthetic or natural, that's mined out of the earth. A conductive additive, like this is where people get into carbon nanotubes, or they'll be looking at carbon black, or conductive additives to help electrical conductivity, and a binder. By binder, which is the term in the battery industry, glue. You got to glue it together, right? And then the anode is then, so these things are mixed into a slurry so that they can be coated onto an electrode sheet or foil. In other words, you've got this chemistry going on in your anode material, your graphite, your conductive agent, and the binder that holds it all together. But how do you get the electrons in and out? So you could see on the left side of this, you've got the graphite layer, and then you see those little E's with a minus on the left-hand side going out. Well, those go out via basically a foil. And in the case of the anode, electrochemically, it happens to be copper. On the cathode side, and what it says there is LiMo, which means a lithium metal oxide. M could be cobalt, it could be manganese, it could be iron phosphate. Well, actually, that's different. That's not a metal oxide, it's phosphate. But again, there's exceptions. It could be nickel, manganese, cobalt. It could be nickel, cobalt, aluminum. It could be, anyway, it's a metal oxide. So in a corollary to the anode, in the cathode, you have this lithium metal oxide, sometimes a conducting agent, and a binder, a glue. Now, there's many other things you can put in there. Now, the cathode foil is aluminum. The anode foil is copper. You know how you're going to remember that? Copper starts with C, it goes with anode, which is A.
Mhm.
Cathode starts with C, it goes on aluminum, which is A. In this case, C goes with A goes with C.
Yeah, that's
Now that
exactly
you've heard
how
that,
I do remember it as well. That's exactly
you're
how
never going to
yeah.
forget it now that I've
Yeah.
said that. But if you try and just blindly memorize, oh, the cathode, is that copper or aluminum? And I can't remember. It's reversed for the letters. Now you will never forget it. So going back to mixing, the first step. Well, actually, no, you can leave that. Sorry about that. Go back to that one. Let's just finish up with what a battery cell, how a battery cell works. So you've got your anode is your negative electrode by convention. Your cathode is your positive electrode. People like cats, it's positive. I'll keep repeating that. And then you need lithium ions, in other words, lithiums that have a positive charge that are missing an electron, moving back and forth. They literally physically move back and forth between these two electrodes. But one of those electrodes, the cathode, is positive, and the other one, the anode, is negative. And if you put them together, just like if you put a piece of metal shorting out your battery, they'll short and you'll get sparks and a fire and it won't work. So you have something in between it called a separator, which you can see in the middle. And a separator is a microporous, it's usually a microporous, meaning little tiny holes, little tortuous holes in plastic. Mm-hmm. Why plastic? It's usually polyethylene or polypropylene. It's plastic because that electrically isolates the cathode from the anode. So you have cathode, a separator, and an anode. You can squeeze those together and the cathode doesn't short circuit to the anode. But the lithium ions can't just hop through air. So you usually put in an electrolyte. In the majority of cases, the electrolyte is a liquid. It's an ionic liquid. If you you could go look up electrolyte on the internet, pull up a safety data sheet, which you can find from somebody. You'll see about 5 different ingredients. There's usually like 12 because there's a bunch of trade secrets. It's a mixture of organic solvents. Why do I say that? I'm not expecting you to know what an organic solvent is. Organic solvents are flammable. An organic material is well, you know what else is organic? Gasoline is organic, okay? And gasoline burns. And organic solvents, in general, are flammable. Mm-hmm. Polyethylene is a plastic. Think of it as frozen gasoline. It'll also burn. It's just not quite as explosive like gasoline. So the electrolyte is primarily usually flammable, depending on the electrolyte you use. And they put some other things called salts in them to help the lithium ions transport back and forth. Think of it as like a boat helping ferry people between the anode and the cathode. The salts are the boat, and the water is the organic electrolyte. Okay, so we got to make this thing. Let's get back at it. You got to make that graphite layer, which is coated on aluminum. I'm sorry, I got it wrong, which is an anode. So it's coated on copper because it's the anode. So it's coated on copper. And then you've got this cathode material, which is coated on aluminum. So let's go to mixing. Mm-hmm. So the first thing that you do, and remember, let's take a basic anode. I said that the anode is graphite, a conductive agent. You're talking very little bit of conductive, 0.5% by weight, 1% by weight, maybe 2%. See, primarily graphite, a conductive agent, and a binder, aka the glue. The standard glue in an anode, and again, always exceptions to this, are carboxymethylcellulose and styrene butadiene, a low molecular rubber. Why two different glues? Well, it turns out that one of them, the CMC, is good at cohesion, which is gluing the graphite to the graphite. And the SBR, the styrene butadiene, is good at adhesion, gluing that whole thing to the foil. It's the anode to the copper foil. But there are other binders and other binder combinations you can use. Now remember, you want to use as little binder as possible, because binder, the only thing it does is glue things together and then take up space that doesn't help you with a battery being a battery. So you try and minimize that. You make it too small and you don't get good adhesion, and your electrodes fall apart, either immediately or 300 cycles down the road. So there's a big sort of tug of war between minimizing the binder content. The other thing, but this is where batteries start to get hard. So you say, okay, well, Ken told me I got three things. I got graphite, I got a conductive agent, and I got binder. Oh, but the binder's really two different binders. Okay, so I got four things, and then I need to mix them all together. Do I dry mix them, or well, no, I need to put them on something that I can coat. So you use water. So you put in water, and you think like, well, if like I'm baking a cake or I'm making bread or something, just put all the ingredients together and just mix them up. Yeah, except that doesn't work. You get really bad batteries when you do that. So there becomes a whole, it's not just science. There's a lot of trade secret and intellectual property that different companies guard very carefully about what order you mix what and how long it has to mix. Because remember, for instance, the CMC is really good at binding the graphite to the graphite, but the SBR is good at binding all of that to the copper electrode. And if you mix them in the wrong order, it doesn't work as well. Your tests will come out the same. Your viscosity tests, they'll be the same. It looks the same. It's a big, dark, black, gooey, liquid mix. But when you get to the end cell, the performance is totally different because you mixed it in a different order. And you're going to say why. And I'm going to say, look, we could go into it, but we'll never get through everything. My point is, and yes, there are scientists that figure out this order works for these ingredients, and the workers on the battery line, you should just hand them their instructions and say, put this in for this long, and put this in for this long, and put this in for this long. And I'm telling you that those people who do that, if they understand why you put one in first and why you put the other one in next and why you mix for a certain amount of time, your production goes better. It's that human element. So the next thing that you do, now that's the anode. The cathode, I don't want to get too detailed. Electrochemically, in a lithium-ion battery, carboxymethylcellulose and styrene butadiene rubber, those things that were soluble in water, are not electrochemically stable on the cathode side. In other words, electrically and chemically, they chemically break down because of the electric potential. So you really usually use a fluorinated binder. It's got fluorine on it, which makes it really expensive. But those aren't soluble in water. So now you can't use water as your solvent. The other thing is that if you're making a high-end NMC battery, lithiated nickel manganese cobalt is very reactive with water. So you do this in a dry room. So you can't use water for that reason either. So they usually use NMP, which stands for N-methylpyrrolidone. It's a little unfortunate that NMP sounds like NMC, which is nickel manganese cobalt, but NMP is a solvent. It is like diesel fuel, not technically flammable at room temperature. It's a great processing solvent. It's not reactive. It's not very reactive with anything. It has a very low vapor pressure. It's great at suspending various types of particles. It's really wonderful, except it's super hazardous to humans. Kind of like lead is great for plumbing connections, except that it's toxic. Like asbestos is an amazing insulator, but is really bad for your lungs and causes cancer. NMP is an amazing processing solvent, but it's really dangerous. So you've got this really dangerous chemical in your anode. You've got water in your cathode. You've got water in your anode. You've made your slurries. They've got their glue. They're this mixed up goo. Now you're going to coat onto your foil. Anode coats. Anode starts with A, coats onto copper. Cathode starts with C, coats onto aluminum. And what happens is there's many different coating techniques, but think of, you almost, extrude is the wrong word, but you have these slot dies usually, and you pump this fluid out and dispense it while the foil is going through this long system. And that long system takes the bare foil, wraps it up through, gets coated with a thin layer, and then that gets run through drying ovens, because you need to now get rid of the solvent now that you've coated it. So when you're drying the water, you just evaporate it. And when you're drying the NMP, because it's toxic and expensive, you need to recover it. So there's different recovery systems. This is millions of dollars in expensive equipment. You need to recover it and then re-refine it. So now you're running a chemical refinery to refine NMP, which is, again, causes birth defects. It's super hazardous to humans. So everyone's wearing face masks and respirator cartridges. The interesting thing, and I'll throw out, I'm not going to throw out all the problems that happen at every stage, but drying is a great example of how complex this is. And this is where science becomes super important. So you think, okay, so I've got this wet slurry, I've coated it on this thing, it's got a bunch of binder glue in it, I just need to evaporate off the water in my anode, and then it'll all be stuck together. And the answer is, yeah, that's true. If you dry it too fast, though, what happens is the water is coming up to, you have this, think of having this layer of wet electrode goo on your foil. And as you're evaporating it, it's only evaporating from the top surface, right? It's not evaporating through the foil. So you have this transport problem where water molecules are moving up through. And what they do, because the binder is dissolved in them, they effectively drag the binder up with it. And if you dry your electrode too fast, all of your binder, your CMC and your SBR in this case, you get, when you're finally dry, most of it's up at the surface and not a lot of it's down at the bottom. And if your SBR is moving up through your, up to your surface, well, the SBR is what holds your electrode to your foil. So now you're going to have delamination problems. And if you move too much of your CMC up to the surface, then your regular electrode doesn't hold together very well. Added to that, now your top layer surface of your electrode has a ton of glue in it. And now your electrolyte doesn't wet well. Your lithium ions don't move in very well. And so the drying regime is super important. This is why your drying ovens are sometimes 70 meters long. 70 meters is a long drying oven.
Yeah, that's right.
And then you say, okay, well, we'll make a really long drying oven, and that's really expensive. Oh, by the way, it's got to be in a dry room because you can't have any water vapor around. Well, for the anode, obviously you can, but for the cathode, you can't.
Okay. So let me stop here, because you mean the drying is in a dry room?
Well, the ovens usually are sealed and don't go through a dry room. And then, so for the cathode, the rolls that get coated are in a dry room. Dry rooms are also very expensive.
That's right.
Then it goes into this oven, which is usually not in a dry room. And then it goes back into a dry room to get rolled up.
But does old manufacturing, because before jumping coating, I'm not talking about LG Chem and Panasonic. I'm sure that they are doing it in a dry room. But does all the batteries which we have in the market really tries, there is any standard to say doing this in a dry room? To my knowledge, there is not. And there are problems which happening because of not doing the process in dry rooms, to my knowledge.
That is true, but there are, like I said, there are always exceptions. For instance, LFP, which is iron phosphate. It's a different type of cathode. There are many manufacturers that actually do their cathode using water. They do an aqueous process because two reasons. You say, wait a minute, Ken, you just said you can't do aqueous for the cathode for two reasons, because because you need a fluorinated binder to be electrochemically stable. And secondly, your lithiated cathode is too sensitive to water. And then I say, yeah, but LFP's voltage is lower. So guess what? You don't need a fluorinated binder in the cathode because the voltage doesn't go up as high, and LFP is not as sensitive to water. So in the case of LFP manufacturing, you can use water as your solvent for your cathode. There's always exceptions. And if you're really quick, you could also get away with not doing it in a dry room.
Okay.
Right? I mean, how much water exposure is too much? Well, this is not digital. It's not like, oh, too much, oh, too little. No, if you expose it to some moisture in the air, what happens? Well, you get some lithium hydroxide, you get some metal oxides. So what? Well, your capacity goes down. That water in there will also react with one of the salts in the electrolyte that'll form hydrofluoric acid, which degrades your anode and your cathode, and your capacity is less and your cycle life is less. And
yeah,
it's not like the cell dies. It's not like the cell explodes because it was exposed to water. It's just not as good of a cell.
Yeah. That's the main point which I wanted to make is that you said dry rooms are expensive, and anyone who works in a dry room, including me, knows that they are expensive. But because there are some audience as well who doesn't know what is a dry room, so let's give a quick definition for it, please. So what are the conditions in a dry room is?
So in a dry room, well, you can define it how you want. In general, the industry standard for a dry room for manufacturing lithium-ion cells is something that has a dew point, and I'll get to defining that, at the dry room temperature of minus 40 C. Meaning at 40 degrees below, if you had a surface in that dry room that was at minus 42 degrees centigrade, water would condense on that out of the air. Now, if you've ever lived, many of you probably have not, in a really humid environment, and it gets cold outside, you'll get water droplets forming on your window because there's a lot of moisture in the air, and it gets cold, and it's no longer the air. When the air gets colder, the water drops out of the vapor phase. What a dry room's definition is that it drops out of the vapor phase at minus 40 centigrade. Doesn't mean there's no water in the air. It means there's not a lot of water in the air.
Yeah.
It's not zero, but it might as well be.
Yeah, I remember the first time I went inside a dry room and see the minus 40 degrees, and we were not wearing heavy jackets by this time. You don't feel that cold inside because of humidity, I believe. So you can work inside in this very low temperature, and it was like a new experience. But I wanted to raise this point to make the aspect related to cost, because we see that we're just in the first steps of manufacturing, and we are talking about huge amount of cost of investment. And I want to translate to people where the differences come, and it will build up, by the way, between a good cell and a bad cell.
Yeah.
So this is one of the things I wanted to stress out.
Yeah. Good cell, less good cell, slightly even less good cell. Again, there's this continuum. And that's the problem. Some people like me, because I was in quality, I say, you cannot let your dry room get above minus 40 C. Well, you can. Your cell performance is probably not going to be quite as good. Is it still going to be in spec? Maybe. I don't know. Got to try it. You can cut corners here and there. And this is, if you were going to cut corners on something, I suppose this is probably where you do it because it's not safety related. But again, if you're already looking to cut corners when you're building a cell manufacturing plant, you probably should not be making lithium-ion batteries.
Yeah,
because you're
I
not
can
coming in
imagine.
with the right attitude.
Mhm.
Again, that's the human element, not the scientific reality.
Yeah,
So, and look, the drying's complicated because, I said it's called binder migration if you dry too fast. But you can actually dry fast at the beginning when it's really wet, and you can dry fast at the very end when it's sort of all stuck. There's 4 phases of drying, and you can dry at different. So you got zones in your oven, and you can adjust the different zones. And depending on your foil speed and the length of your oven and what your binders are and what the size of your particles are, you can change your drawings. It's super complex. Every stage of this is super complex. All right, so let's get out of drying.
yeah,
Because we could spend 2 hours on drying. Like
yeah.
literally, I could talk for 2 hours on drying. You don't want to hear about 2 hours of drying. And I'm not trying to scare you by telling you how complex it is. I'm trying to demonstrate that this is a very complex process. But what that means is there's lots of space for you to become an expert in an area and be super valuable. Like when we get to the career side of this, right? It's not like you're injection molding a plastic thing and there's 20 million experts out there and you have nothing to bring to the table.
Mm-hmm.
No, we have an industry with a super complex set of problems, and you could become an expert in any one of them.
That's right.
Or helpful in any one of them and be helpful. No one person, certainly not me, understands all of these processes well.
Exactly,
No
and this is a very important message, Ken, because people think that, yeah, we will discuss it in the career part, but just a quick comment on it. The mentality, especially that we have in the Middle East, is that some people in general tries to understand many things and say, okay, we will be good if we understand many aspects of the thing, how it works. There is the culture of specialization or having just one aspect to the depth it needed. So someone who's called a drying expert, you will not find rarely those people in the Middle East area, but it's easy to find them, for example, in Germany, in Japan, in the US, in specialized nations. You will see people who are really spending 10, 20 years doing the same thing again and again. And just every day they get just a little bit of step. And if you ask them about coding, they will tell you, I don't know the answer, even that if they know it, but they will never jump out of their specializations. So this is as well something which is, it's like not a common sense culture, I would say, in the Middle East, because I come originally from Egypt. But I did see this because I live in Germany. Of course, you know how the German people as well, they are like the Japanese people, they are very specialized. So this is the main culture here. And this is really a very strong message, which we need to deliver to everyone who's hearing us today before jumping to the next one.
Sure. So let me get to calendaring. Let's get through this, because otherwise we can go on forever. So calendaring, some people call it pressing. It's the term people use. I use calendaring. Other people I've talked to call it pressing. It doesn't matter. It's basically 2 giant steel rollers that here we go. That you run through here. Here we have a top roller and a bottom roller. They can be heated, they can be cooled, they can be heated and cooled, they can run at different rates. Generally, you don't do that. And what you're doing is you've coated on this electrode, you've dried it, but now there's a lot of pores left over because you basically evaporated out the water. So it's a little too much like a sponge. And that's fine if you don't care about high energy density. But if you do want to pack a lot of energy into your cell, you need to control the thickness of those. And calendaring is basically you are crushing. I mean, these are big rollers. Mm-hmm. You are pressing the ever-living snot out of this electrode to a certain level of density. Now you could say, oh, well, let's put more energy in my electrode. Let's crush it even more. Well, then your pores become too small and you can't get your lithium ions in and out. So there's a balance there. If you crush it less, you get lithium ions go in and out faster. It's faster charge and discharge, but you fit less energy, total energy in your cell. If you crush it more, now you can pack more electrode in your cell, but your charge and discharge rate, how fast you can charge, how much energy power you can get out, goes down. So there's a trade-off, and that's all part of the cell design. When you design your cell, that's all considered. And lithium-ion cells that go into like a power tool, like a drill, generally don't have as much energy as the one that goes in your car, but they have more power per cell because they're designed for power tools. It's not the same cell. So yeah, that's calendaring. We can just at the end of that, and of course all of these steps have multiple quality control steps. Beta gauges, looking at thickness, and people cutting out little pieces and doing moisture tests on them to make sure they haven't been exposed to too much moisture, and adhesion tests to make sure that your adhesion is good to your foil. And yeah, there's tons. Yeah, I'm skipping by all of the different quality control steps, which are also all areas of expertise that one of you could become an expert in. So the slitting, generally, yeah, I mean, this is reasonably accurate. When you're coating, for instance, take it that lower lane where it says prismatic and cylindrical, and you see that the coating is actually in little lanes. You can do that, or if you're doing prismatic, you might just have one lane, but then the left side would be an electrode and the right side would you'd slit it down the center. Now remember, when you're coating these things, if those edges, you'll have high edge problems, you'll have low edge problems, you'll have width problems. All of this stuff needs to be in specification. Well, how close does it have to be? Oh, 0.5 millimeter. You're sort of, you better not be off by more than 0.5 millimeter, or you're in a lot of trouble, and it can actually become a safety issue. So, when you're slitting it, your little knife blade sticking down, literally slitting this, if your slitter cutting wheel isn't sharp enough, you could get a little metal burr that sticks down. And if that burr sticks down 70 microns, remember, 100 microns is 0.1 millimeter.
Yeah.
So if you have a little metal burr that's 1/10 of a millimeter long, that is a serious safety problem. You'll probably catch that in formation and aging when your cell catches fire. But really, you don't want those happening. So we are talking about very exacting tolerances. And you say, okay, so this goes really slowly, and you're really, no, it doesn't go really slowly. These things are moving at 20 meters a minute. And sometimes when you're slitting cylindrical cells, you could have 7 lanes. So 7, 10, 12 of these slitting wheels are slitting, and they're all getting rolled up separately. And every single slitter has to not make a burr bigger than 10 microns, 20 microns. Remember, 100 microns is 0.1 millimeter. So you're talking really more like 100th of a millimeter is really where you'd like to be on your burr size. 100th of a millimeter.
Yeah.
Okay. I could go on about
I would just like to give a very quick overview about pouch, prismatic, and cylindrical cells. Who doesn't know what is pouch prismatic, I have a picture here, and we will jump back to continue. So I have a cell format here. I guess I can use this one here from the cell formats. We can use this one. So this is basically a pouch cell. So it's like this type of cell which we have, for example, in our cell phones. This is a prismatic cell, which is hard case cell, and this is a cylindrical cell. So this is exactly what was mentioned in the other side. Those are the 3 common types which we have for lithium-ion batteries, more or less. So I just wanted to show this because it was mentioning here the 3 aspects, and I will jump back to
So once you've gotten your electrode made, which is the hard part, in my opinion, here's an interesting little thing. People look at all these steps, and we'll go through the cell assembly steps. And when you walk through a lithium-ion manufacturing plant, if you ever get the opportunity, it's fascinating. And it's interesting because everyone seems to think that the cell assembly, this is from the slitting on, is the hard part.
Mm-hmm.
And yes, cell assembly is really hard. But I think, and they all sort of dismiss electrode production. And that's because you mix a bunch of stuff together. It looks like black goo. You coat it onto a foil. It looks black. You press it down. It looks black. You slit it. You're like, how hard can it be? But there's all these chemical nuances in there. But people can't mentally grasp what's going on a molecular level, so they don't think it's hard. The cell assembly, when you see cell assembly equipment, and you can go watch YouTube videos watching like stackers, like go look up, Z stacking video on YouTube. You'd be like, oh, that's really complex. And the thing is that we all as human beings can look at that. We can visually see how complex that is. So we say cell assembly is really hard. It is hard, but it's not as hard as mixing and coating. Because you don't get that visual feedback of what's going on in mixing and coating. In my personal opinion, the hardest part of cell assembly is the electrode production. It's the mixing and coating, because you can do it. It's not hard to do it. It's hard to do it right.
Mm-hmm.
But it's very hard to tell if you've done it right. The second hardest part is formation and aging.
Yeah.
Which people also dismiss, because you can't see what's going on, and it's molecular. The easiest part is cell assembly, which is still really hard, but everyone thinks it's the hardest part because you look at all these machines doing their little fancy machine stuff, and you're like, whoa, that's really complex. Yeah, it is. Trust me, it's not the most complex part. All right, vacuum drying. So you will then generally vacuum dry to make sure any water, you want to make sure, again, you don't want water in your cell. You want no water vapor. So you will vacuum dry. That actually serves two purposes. Gets rid of any residual solvent that might be left, especially in the anode, because in the anode, the solvent was water. Okay. And sometimes people dry cathodes. Sometimes they don't vacuum dry cathodes. Sometimes they vacuum dry it to get rid of a little extra NMP. It depends on your manufacturing system.
Okay.
Some people do not vacuum dry cathode. Some people do. And is there a right or a wrong? The answer is depends what your other systems before that were. Depends if you were using a dry room. Depends who your material supplier is and how good their supply is. Depends how your oven works. Depends. But anode, you definitely dry. So after that, we now we move into cell assembly.
Yeah,
and cell assembly. Go ahead.
Yeah. Will be more meaningful for the people, I guess, because yes. This is what they see in videos and so on. I guess so. I believe so.
Yep.
Yeah.
Cell assembly. So in a cylindrical cell, you take your anode and your cathode and your separator, and you wind them all so that you have separator between your anode and your cathode.
I guess I have one. Yeah.
Yeah. Wait. It's okay. I imagine it. You're rolling it up like you're rolling a cigarette or a cigar, and it's a spiral with anode and cathode and separator all wound up. But there's also, you got to add tabs, because how are you going to connect this stuff? So on your anode and on your cathode, there will again, there's the exception. There's Tesla's tablets. I know. But generally on your electrode foil, the copper for the anode or the aluminum for the cathode, you will literally weld on with usually a resistance weld, a tab. So a little piece of metal that sticks out. And then on the anode, that will get bent in on these jelly rolls. They're small. So it gets wound up super tight, all wrapped up in separator. And then this gets inserted into a can. So it gets, wish I had some demo pieces. So if this is my can and my jelly, this was all rolled up, it would get inserted. Okay, but I got to connect it. So you'll have a stake down the center, which welds your anode to your can. And then on the top, well, you'll leave it open because you got to fill. Eventually what you'll do is you weld your cathode tab to your top cap that'll later get crimped. You'll weld that little tab to your top cap that'll then finally get inserted and crimped into your cell.
Mm-hmm.
I need better props. But, you know, every one of these steps, the welding has yield problems. The insertion has yield problems. The winding has yield problems. You know, the alignment of the anode and the cathode, the X-ray of the system to make sure that your alignment was right. Because now once you've inserted it, you're blind. Then you do, yeah, I suppose you could do flanging. You'll make a little, for cylindrical, that cap needs to sit on something. So you do grooving or beading or flanging, whatever you want to call it, where they put a little shelf in the can. So you come in with a little, it's almost like a blade as this thing spins, and you put a little groove in, which is what the cap will sit on. But before you put your cap in, you need to get electrolyte in. Electrolyte, remember, is this liquid medium by which lithium ions can transport back and forth. They don't just hop through air. Not that there's a lot of air in there, but they do need some transport medium to swim across, basically. So you put in electrolyte. Small cylinders are pretty easy. The electrolyte soaks into the anode, the cathode, the separator, because they're all porous. Happens fairly quickly. And then eventually, well, okay, let's leave it at that for now. For both prismatic and pouch, there are generally two ways in which what we call jelly rolls are made. So this, before it goes into a can or the final pouch, it's called a jelly roll. Probably because cylindricals looked like little rolled up jelly rolls. One way that it's done, here's the where it says prismatic. You see it says winding flat. So basically, you do the exact same thing. You spin up this wound assembly, and then you flatten it. You smash it down, so that if you can zoom in on like that hot pressing part. Now it's hard to see, but you can see that when you smash it down, it's almost ovally. You know, it's because you've collapsed this thing. It's got rounded edges. And that's probably the fastest and the easiest way to do it. The other way that people do it is what you would call stacking. And he's got stacking shown by the pouch, but you can do it for prismatic too. And there's two different kinds of stacking. You can do Z stacking, where basically your separator goes back and forth, and you place an anode, place a cathode, place an anode, place a cathode, like building up layers of a sandwich with separator weaving in between. The other way is some people will take discrete, they'll put an anode, a sheet of separator, a sheet of cathode, a sheet of separator, and they'll stack the whole thing up like a sandwich. Now, how hard can this be? Oh, go watch some videos. Go watch some videos of Z stacking on the internet, and you go, "Wow, those things are going in really fast." But here's I'll go off on a tangent for a moment. You want to maximize the amount of energy in your cell because you're going through the expense of building it. So you want to fill as much of that volume as you can. There's a failure mode that I don't think we'll get into. But basically, your anode needs to be bigger than your cathode, both in terms of how many lithium ions it can accept and geographically. In other words, it needs to overlap. So if you take a cylindrical cell, lithium ion cell, and you discharge it, and you get in a fume hood, and you unwrap it, you'll see that the width of the long anode is wider than the width of the cathode. And if you take a prismatic cell, or the sheets, if you were doing singular sheet stacking, the sheets of the anode are wider and longer than the sheets of the cathode. And that is a safety related issue. And you say, okay, great. So when we stack them, we just need to make sure that everything's centered. You go watch some of those videos and watch how fast those sheets get stacked. And now I'm going to tell you that on a not great quality cell, the anode might be 2 millimeters wider than the cathode. So you have maybe plus or minus 0.5 millimeter of alignment on all 4 sides, corner to corner. And you watch these stacking videos, and it's stacking these things at sheets per second with sub-millimeter alignment accuracy. Now, it's not done by a person, it's done by automated machinery. But if it gets it wrong, how do you know? Because that's a safety issue.
You will know when the cell. I guess you will know when the cell explodes. Yeah.
Oh wait, have I lost you on audio?
No, I was okay. I was saying that you might know when it's too late, when the cell really explodes. But we can still hear you, Ken.
Uh-oh. I think we lost audio. Can you guys hear me? Say something.
Yes, we can hear you.
Okay, sorry, I lost audio. Where did you lose me?
No, I was just saying that you will know when it's too late, when the cell maybe goes into thermal runaway or explodes.
Yeah, but the problem with misaligning stacked sheets, I see there's actually a question that we should I'll get to. The problem with misaligning stacked sheets is it might not show up for a couple of years, and then your cell catches fire.
Exactly.
Years. So then you have inline X-rays and inline CTs and all sorts of. Anyway, I'm just pointing out it's not easy. And if things don't get stacked right, you throw away the entire cell. What was the question?
There was, I guess someone needs to ask a question. Ali, you can unmute yourself, and if your question is related to this part, please do it.
Okay, let's go on. If you've got a question, you maybe throw it into the chat, Mohammed. You can grab it out of the chat and ask it. How's that?
I would do this, yeah.
Yeah. Okay. So after you've made this jelly roll, which hopefully while you're handling it, sometimes you hot press it to try and get it to all stick together a little bit, but you can't use too high temperature, you can't use too low temperature, depends what separator you're using, it's very complex. Then you insert it either into a pouch for a pouch cell or into a can, meaning usually an aluminum can. You might need to weld it to a lid first. It depends on your design, and then you need to seal it in a prismatic cell. You're usually laser welding your lid to around the rim of the can, and if your pouch you're doing a heat seal. You're not completely sealing it because now we've caught up with the cylindrical. Now you need to get that electrolyte in, so you got to fill your electrolyte. Now, on a small cylindrical cell, that electrolyte you put in however many grams you're going to put in, 4 grams, 7 grams, depends on the size of your cell. In a giant prismatic cell, like some of these big cells, you've got a tiny little fill hole. And so you put in all the electrolyte you can, and you can't get in enough because it hasn't soaked in, because there's a transport problem. This is not like soaking water into a sponge, which, by the way, also takes time. But imagine that you have a giant sponge in a package and you put some water in one part, it's going to take time to soak through. And until it soaks through, you have 2 problems. One, you can't get your electrolyte in. You can't get enough electrolyte in because you need to get in a certain amount. And the other problem, so sometimes electrolyte filling can take 30 minutes.
Okay.
and you pull a vacuum, and then you put pressure, and you pull a vacuum, and you put pressure, and you pull a vacuum, and you put pressure. But remember, electrolyte is flammable, it's toxic, it's hazardous, and it can't be exposed to water.
Yeah.
So all of this is done in a dry room.
I have a feeling. Yeah.
So let's pretend you've gotten all the electrolyte that you want in your cylindrical cell or your prismatic cell or your pouch cell. You say, okay, great, now I can seal it up. Nope, no, you can't. Then usually what you do before you do the final seal is you do a pre-charge where you charge up your cell a little bit. Usually, depending how long sometimes you charge up to a certain lower than full voltage, sometimes you go up to full voltage. And what happens is now you're starting the first form of the cell. You got to make sure all the electrolyte's soaked in. So sometimes soaking can take 30 hours. On large cells, you might have to wait 30 hours at an elevated temperature. Then you do this pre-charge, which is like the first stage of formation. And what happens in that, your electrolyte does some electrochemical degradation on the anode. It creates what we call an SEI layer, which a solid electrolyte interphase. Some people call it solid electrolyte interface. I think phase is the correct term, but people use them interchangeably. There's no standard. This SEI layer happens. You can't stop it, but it also turns out to be a protective mechanism.
Yeah.
But when an SEI is formed, you also get gas given off. It creates gas. And the problem is if you fill your cell, seal it up, and then send it directly into formation and aging, that gas will blow up your cell like a balloon. So you have a degassing phase, which is sort of this pre-charge plus putting it under vacuum to pull the majority of the gas off. Then you seal your cell. So for instance, you might put a little plug in it and laser weld it shut. But remember, you're now laser welding a cell that's got flammable material in it. And it's partially charged. So sometimes bad things happen.
Yeah.
Let's leave it at that. Then you go into formation and aging. Formation and aging is where you're doing your initial charge and discharge cycles, because it's not really a battery until you've charged it up and discharged it and charged it up a couple of times. And let it sit to let more electrolytes soak in, and let it sit to let the SEI layer, the solid electrolyte interphase layer, form. And it's basically a series of very slow charges and very slow discharges. And then sometimes you let it sit for 24, 48, 60 hours at high temperature, depends. Well, what should I use? A lot of trade secret in there. I don't know. What's your anode? What's your cathode? What electrolyte did you use? What's your cell design like? Depends. There is no recipe. I mean, each company has its recipe, but the formation and aging can take anywhere from 2 to 7 days. And because a lot of that's just letting the cells sit. But 2 to 7 days, when you're doing, let's say you're Panasonic at the Gigafactory in Nevada, and you're doing cylindrical cells. All right, they're not that big. Let's say you're doing 1.5 million cells a day. Well, if your formation and aging took 10 days, I'm just making that up. It's not what it takes, by the way, but I can't tell you. And you're doing 1.5 million cells a day. That means you are holding 15 million cells in volume during formation and aging at any given time. That's a lot of space.
Yeah.
That's a lot of energy. That's a lot of time, and that is really expensive. So energy-wise, usage-wise in these things, the real energy killers are the ovens when you're drying your electrode and the formation and aging.
Okay.
Those are real energy killers. which is one of the many reasons that people try and site these factories by areas with really cheap electricity. Because the electricity that you use to run these operations and the dry rooms and all that, I think the third is the dry room. The third largest electricity usage is probably the dry room. Dry rooms themselves, just dehumidifying. Of course, you use less electricity to do that in the Middle East. That is for darn sure, because your natural air is drier, so it costs less to dry it, right?
Yeah.
To dehumidify it.
And the good thing is that there is sun, so you can build a solar power plant beside your gigafactory. That's
100%.
cool, huh? Yeah.
100%. It's like a self-licking ice cream cone.
Yeah.
So once you've been through formation and aging, there's a bunch of testing. You might wrap your cell. You might put a sleeve around it. Some people don't put sleeves around it. You sort of do a final testing and inspection. There's all sorts of quality control steps here as well before they go out to either your customer or to your next process line. It's you weigh them. Was there enough material? And all these cells get weighed multiple times. So you confirm that you got enough electrolyte in because you know how much your can weighed, you know how much your jelly roll weighed. You confirm that the voltage is right. You confirm that there hasn't been too much self-discharge, which would indicate you have a short inside the cell. You look at the internal resistance. You look at, there's a million things that you check, but you've been checking these things all along. I have completely missed all of the quality steps, which as an ex-quality guy is probably an egregious foul. But we could spend 3 hours just talking about quality checks. And then you package them up and you ship them. I wish it was that easy because it's not. But
yeah, it's not. But before we ship them, I would like to have, because once I heard that from you actually something about formation. It was funny to hear that formation is the phase where a lot of gigafactories get burned, or a lot of cell manufacturers facilities get a lot of fires in this phase, right?
So if you have, let's say, a defect in your cell that didn't get caught earlier, maybe a little burr sticking out, and during charge and discharge and formation aging, things swell and they relax and they swell and they relax, and you get that little short, you can get a fire. Now you could say, well, I'm going to have great manufacturing. I'm not going to have a cell defect. I'm not going to have any fires. That's what everybody tells themselves. Everybody gets badly fired. The thing is if you accept that, you don't have to like it. I mean, you obviously try to never have a fire in formation and aging. You try to never have a fire anyway. But formation and aging equipment is set up for this. There's inline, it self-detect when there's a voltage short and it pulls things out, and there's robots that come in with firefighting equipment and robotically spray it down. And there's, good formation and aging equipment is basically predicated on the assumption that at some point, maybe once a year, maybe twice a year, you're going to get a fire. And the key is to just not lose your whole factory. And there have been many factories over in Asia where entire factories have burned to the ground in the early days of lithium-ion batteries. And then we learned, and we put in firefighting equipment in the formation and aging equipment, and it's fine, right?
And I hear that the formation now is like most factories really split it as in a separate building, even the formation and aging, correct?
Yeah, you will either put formation and aging in a separate building so that you do not lose your whole building. Although again, with current equipment, you shouldn't lose your formation and aging building anyway. Here's what happens. A cell catches fire. That's okay. There was a defect. Now you're set up for a long investigation, because you don't just go, oh, it caught fire and move on. Now there's this triggers all sorts of investigations, but because you have to figure out why. How did we miss a defect, right? But a fire happens. The operator gets notified. They put on whatever protective equipment they need. They evacuate the people who don't need to be there. The robots go in and they do the firefighting, and then you might have to go in with an extra blanket and pull out a cell or drop it in a dunk tank or whatever it is. It doesn't need to be a reason for panic. I mean, like if a house catches fire, yeah, you should panic and you should run out. Well, you shouldn't panic, but you should run out. But the firefighters run in, right? Because they know how to deal with it, because they're firefighters. That's
Yeah.
what they do.
But
They're
this
like,
is,
oh,
but this is,
look, fire, here I go.
yeah, but we have to emphasize here that we are talking about the level of Tesla, Panasonic, and LG Chem. This is the Mercedes manufacturers, huh? So in this case, the firefighters are trained. In this case, you can fight it. In this case, you can do it. But unfortunately, we see in many countries, especially in Asia, India, and this region, there are disasters which happening because of manufacturing problems and people not dealing with fires in a good way in the facilities, or thermal runaway along the street. But I guess I wanted to emphasize this formation point because I remember it was one of the things I had in mind since I heard it, that it's not an easy phase to be done even. And the second question which I have is that some people, I heard that they get dry cells from a manufacturer, maybe an Asian manufacturer, Chinese manufacturer, and they do just the last phases. So is it feasible to do this? So just to relate my question to the process, they just get, I guess, to this phase here as a cylindrical cell, and then they do the electrolyte filling and the formation and everything, sealing, cleaning, and so on.
Sure. Yep. There's companies that do that. It depends how you split up your manufacturing. There's companies that start at cell assembly and they just get coated electrode rolls from a manufacturer.
Mm-hmm.
It depends how you want to set up your operation. I do want to say one thing just so I don't get misinterpreted. I am not being flippant. I'm not being casual and cavalier about cell fires. When a cell fire happens in a formation and aging, and it will happen, it's just a fire, you deal with it, but you are trained to deal with it. The fumes given off by a burning lithium-ion battery are super dangerous. The people dealing with it are wearing full face mask, respirators, and protective equipment. If you have, and I say that because if there's, you've got a e-bike or a e-motorcycle and the battery catches fire in your house, do not breathe those fumes. That is not a standard fire.
Yeah.
Okay. So I want to be super clear. I'm being a bit, oh, don't worry, it's a battery fire, happens all the time, formation and aging. Well, yeah, asterisk, if you have the right equipment to keep yourself and your coworkers safe while you're fighting it.
Yeah.
I'm not saying, it's a battery fire, don't worry about it. Just go pick it up and roll it up in a blanket. Because if you breathe those fumes, you can permanently damage your lungs. Permanently. There's no hospital that can do anything for you.
Yeah.
You will have breathing problems the rest of your life. Super serious.
Yeah, that's the point. Thanks a lot for emphasizing this, because I always say if you see white vapor comes from outside of the battery, you have to run fast. If it's black, you have to run, but not very fast. So this is my code, which I always use. If it's white, you have to run very fast. If it's black, you have to run as well, but in a lower speed it's allowed. So people really have to have the right way to do it, and in factories, in gigafactories, for sure this will happen. I just want to ask about this cleaning stage here, because I guess I did not exactly understand how important is it to clean the cell. Is it does it have to be done as well accurately, or it just
there's the cleaning. Well, the cleaning / washing. So you remember, you usually get little bits of electrolyte residue on the cell, and so you need to wash those off. So they'll literally wash a cell in water, sometimes water and detergent. It depends who's buying the cell, what level you clean it to. It depends if you're self-consuming it into a module via robots and how much you need to clean it. Electrolyte residue can be corrosive. Well, first of all, it's hazardous to humans, so you want to wash it off. It really is good. How much and how you clean it really depends on who you're selling it to and how they plan to use it.
Okay. Yeah.
I mean, the general assumption in a battery factory, even on a finished cell, is you never handle it without gloves.
Mm-hmm.
That's just, you probably could pick them up with bare hands and be fine, but the problem is that always true? And so you have a standard. You just use gloves.
Use glove. Okay. Yeah.
I myself have picked up an 18650 and shorted it on my wedding ring.
Mm-hmm. Yeah.
Because I wasn't thinking, because I was careless and I wasn't following the rules.
Yeah. It did happen to me with a build before. So
Yep.
even a build can short a module, and then you will never recognize it because you will think you will work. As you mentioned, people think, okay, I'm a good producer. I will not have fire in my formation or aging, or I will not have fire in my battery. But a good battery design or a good factory design will put a probability that I 100% will have a fire. It's the same of handling a battery that people really. I see myself, especially in the Middle East, people really handling lithium-ion batteries like they do with lead-acid batteries, without any way of self-protection, and they think it's an easy thing to deal with. And this is the main message, one of the main messages which we have to get through here. That as well, it's not easy to deal with them.
Don't take this on the Middle East. This is everybody.
Yeah. Yeah, that's correct.
This is not a Middle East problem. This is an America problem. It's a Canada problem. It's a, Africa problem. It's a Europe problem. And people will generally learn more and more. But it's a problem for everybody.
I totally agree. I'm just giving an example of what I'm seeing, basically, because we have a peak of EVs infiltrating the market, and people are get exposed to batteries, and they want to know what is inside it and to open and think about it. But let me first thank you for this crash course about manufacturing. I guess what you shared with us is worth a lot. Really, it's really worth a lot to have such an overview of manufacturing step by step for different types of cells. I guess the people working in the industry will know how valuable it is to share such a knowledge. And I will open the space always for questions. If there is any question or anything related to the process which we did go through, even if there are questions online, we can take them. But I don't know if you need to add any last words about those steps. I guess the main messages which I get out here, I was writing really what you are saying as a note, is that accuracy is a major role. It's very energy intense process. It's very investment, so it needs really very high capital investment to be done, and it's not enough as well to have the right equipment. You need to have the right people who are running the equipment, and you have given us many examples of this.
And it takes time to learn to have you could have the right people who don't know the process. And it's just, this is why I have yet to hear of a gigafactory getting set up that wasn't complete chaos for the first year.
Yeah.
It's just the nature of the beast.
Mm-hmm.
I would say the other thing is, this is any one of these steps, and I've skipped by steps, right? Any one of these steps is a 2 to 3 hour discussion. Laser welding. I could go on for 2 to 3 hours on all the problems with laser welding. I lid to a can, literally. And so, but I mean this, and maybe I can't remember what section you wanted to do next, but this gets to then, wow, if somebody's there saying, I see that there's going to be, I hear that there's this huge job need for people in lithium ion batteries. I'm an engineer or a scientist or an operator. I'm somebody who does assembly, and I want to, what do I need to learn to get into this? And the answer, and you're not going to like this answer, is, well, you should know the generalities, which are things like talks like this. But if you're an engineer and you want to be a process engineer, you're going to have to specialize in something. Mm-hmm. And it could be laser welding, in which case, laser welding aluminum is a science unto itself that has nothing to do with lithium ion batteries. It's just a process that resistance welding, ultrasonic welding, ultrasonic welding, the battery industry did not invent ultrasonic welding. They just happened to use it, right? Roll to roll processing. Battery industry didn't invent that. The paper coating industry invented that, right? Mixing and some of the other stuff is a little bit more, formation aging is definitely very specific to batteries. But, you know, as a great mechanical engineer, you don't need to know cells. You need to be a great mechanical engineer, or as a great chemical engineer, or a process engineer, or a quality engineer. And I'm using engineer just because that's what I'm most used to hiring. But you know, I've also hired technicians and operators, and I guess let me just run with that and say something about what I've looked for when I hire somebody and some of my frustrations. And I'm going to talk about some of the higher education positions, but I'll also then go down to sort of the entry level stuff. So when I'm hiring somebody to be a chemist in a lithium-ion battery company, what I actually want the most